I'm your Skeptics speaker tonight. I'm going to be telling you about a project that I'm involved in. I'm a grad student at Harvard, and I'm with a group that studies the sun. And we had a unique view of the solar eclipse that just happened. We saw it from an airplane above 40,000 feet. And so I'm going to talk about why we did that, how challenging it was, and what we saw. So thank you. And so this is probably going to be interactive, so I'm going to try to get you guys to give me some feedback during the talk as well as after. And feel free to raise your hand and ask questions in the middle of the presentation if you want to. Okay, so does this eclipse map look familiar to anybody? You may have seen it. This was kind of a big deal, right? This is the most recent total solar eclipse, which crossed the whole United States. And up in New Jersey, you guys only saw a partial eclipse, but there were a whole lot of people all along this whole path, probably something like 50 or 100 million people who traveled to see a total eclipse. Did anybody here see the total eclipse? Yeah?
Yes.
Was it awesome? Did you? Yeah, okay. You saw it too? Okay. What did you think?
It was cool.
It was cool, right? So we also saw the total eclipse. We were right around western Kentucky, and we were in an airplane. So I'll talk about the airplane a little bit more later, but it's a special scientific airplane that we built a telescope for. And we flew at 47,000 feet and looked out the window at the eclipse. So does anybody know what's visible during a total eclipse? You wouldn't have seen it with the partial, but what's special? What can you see during a total? Does anybody know? Something to do with the sun. Do you have a guess, maybe?
Corona.
Yeah, exactly. Do you know? Can you tell me what the corona is?
The light that comes off.
Yeah, it's the light, right? It's like kind of on the outside of the sun. So it's actually the sun's outer atmosphere. So the part that we see every day is closer in. It's called the photosphere, and it's really, really bright. So I think I have a picture here. So the photosphere, here's the photosphere. This is the disk of the sun, which we see all the time. Here it's just starting to eclipse. By the time it gets to fully eclipsed, that really bright part is completely blocked out by the moon. And so the corona, which is 1,000,000 times dimmer, and so we can't usually see it because our eyes and our instruments can only get the light coming from the much brighter disk, is actually visible. So the moon is a perfect, what we call a coulter, so it actually blocks the sun. So here's the geometry of the eclipse. So here we are on Earth. There's the moon, which is much smaller than the sun, but much closer. And we're pretty lucky in the fact that in the sky, they have kind of the same apparent size. So depending on how close the moon is to Earth, the moon can be a little bigger or a little smaller than the sun. And when there's a total eclipse, it's a little bit bigger. So it completely blocks the bright part of the sun, and we get to see the corona. And so this is a really exciting time for scientists. This is something I found out kind of recently when I started doing this project, that not only is it really cool to look at the corona during a total eclipse, just for anybody, it's an important time for scientists to study it. You only get a few minutes, but it's a really opportune time to see the outer atmosphere. So I'm going to tell you a little bit about the corona. So here's a picture of it. This isn't the most recent eclipse. This is an older one from a few years ago. So the feature of the corona are these things called streamers. And so you can see there's a lot of structure out here, and there's these kind of wings that go off. Does anybody have a guess as to what might be causing them? What's causing that kind of shape? Does anybody know? Or sorry? Heat? You're right that the corona is really, really hot, right? That's one of the mysteries. It's 1,000,000 degrees versus 6,000, which is the surface of the sun is. So heat is involved in those structures, but it's not what's actually driving them. So what's actually driving them is the same thing that's driving the heat. So it's actually the magnetic field. So have you guys ever played with a bar magnet and iron filings, and you can kind of see the magnetic lines come out? If you do that? So the sun is very similar. So here are the magnetic field lines, and here's the corona kind of just tracing them out. And so you can tell your typical bar magnet, if you've ever seen that, has kind of a nice magnetic field. It's called a dipole. It just kind of goes like this. The sun's magnetic field is much more complicated. There's all kinds of crazy stuff going on here, loops and then lines that go straight out. It's a lot more complicated. And that's because the sun is rotating. And as the sun rotates, you take kind of a nice straight magnetic field like your bar magnet might give you, and it twists it all up. And so I have a little demonstration here. Hopefully it'll work. And I'm going to show you what happens if you twist a magnetic field up. So imagine that this loop, this is one of the loops here. Like, let's say this is this loop, right? So maybe it's anchored here in the sun, and then it goes up into the sky. Can everybody see this? So what happens is these are waving all around, and sometimes the magnetic field lines get really close together, and the magnetic field lines can't cross, right? But what they can do is what's called reconnection. So what they can do is you have two field lines here that will get kind of clumped together, or very close to each other, close to touching, and two here. Right, so now we're almost touching, and it turns out that what they want to do now, instead of having your big outer loop, you end up with two smaller loops. So the magnetic field lines break apart here, they form these two little loops, and that changes then what that structure looks like on the sun. So let me show you what happens when I do that. So I'm going to cut it right here, right, and we're going to form these two little loops. Right, so you can see things kind of shot apart. It wasn't the springiest rubber band. But so what happened? What made the rubber band move? What did it need to do that? What was released when I did that? Energy, yes. So one of the things that the magnetic field on the sun does really well is it stores energy. And just like the rubber band, actually much more dramatically than the rubber band, it can also erupt, right? And so this magnetic reconnection happens where you get the two little loops forming out of one bigger loop. The energy is released. And these are three examples of eruptions that happen because of the magnetic field. So they're just going to play over and over so you can take a look. In this case, and so these are all due to the magnetic field lines breaking apart and then releasing energy. Here we see the energy is released as light. That's called a solar flare. Here there's this is called a solar filament. It's kind of cooler material that's suspended above the surface of the sun, and then it can erupt. And then this is what's called a coronal mass ejection. And so when this happens, it's actually an injection of plasma. So the sun is made up of plasma, which is ionized gas. So gas that has its electrons stripped away from its atoms. And it's an injection of that ionized gas out away from the surface of the sun. And it travels at about 1,000 kilometers a second, which is really fast, can reach the Earth in a day, and can actually affect, this is what causes the aurora, right? So if anybody's ever seen the aurora at the North and South Poles, this stuff getting launched off the sun can come in, interact with the Earth's magnetic field, and then make the aurora appear in the sky. It can actually affect the power grid. It can be actually kind of harmful to astronauts and actually to airplanes if they're taking polar routes. Those are especially affected by events like this, and sometimes the pilots will actually change and take a different route if they know that something like this is happening. And so you can see that, and this is all driven by the magnetic field again. So you can see that, we probably want to be able to predict stuff like this, right? This is called space weather, so it's weather from the sun. We want to be able to predict stuff like this, and that's really, really hard to do. So to do that, we need to be able to measure the magnetic field in the corona, and that's a tough thing to do. And the way that we would like to do it is to measure the light emitted by the corona, right? Because the magnetic field isn't really something you can sense. You always need something else to trace it. You either need your iron filings, which you sprinkle on, or you need to see, like those loops that I showed you. And so what we do is we use light. And so we measure the light. Some of this might be familiar. This is going to be the most technical part, and then I'll get away into more Eclipse stuff. But just to give you some background, you may have seen this. When an electron loses energy in an atom, it emits light, right? It emits that energy as light, and it's light of a very particular color. And so we see it as a particular color of light here, and it's due to this electron jumping down in energy. And so I'm gonna pass these out now. So I don't know if I have enough for everybody, but just pass them back, and if you just have one for every 2 people or so, just go back straight, or here, I should use more than one. So if you hold these up and look at the lights, if you look at a fluorescent light, you might see some of this stuff happening. So you might have to look, so try to get them so that everybody has kind of one nearby. So what do you guys see? If you look at the light, but then a little bit to the side, can you kind of see a rainbow? Does anybody see a rainbow? A million rainbows? So if you look at a fluorescent light, I'm not sure which of these are fluorescent. It looks like not all of them are. If you look at a fluorescent light, you're seeing exactly this. You're seeing an electron jump down and emit light of a particular color. And you'll see a very sharp line. If you look at like a light, like a regular old incandescent light bulb, it looks much smoother. But that's going to become important later because that's actually how our instrument works. All right, so you guys can have fun with those. So in the presence of a magnetic field, we see these colors shift a little bit. And so that's what we're looking for. So we wanted to build something that looks at the colors and then sees them shift. And so this is what we built. So it's called the airborne infrared spectrometer. And I'm going to dissect that name, right? So I'm going to go through each part of it and talk about what it means. And so we'll start with the last word, the spectrometer. Does anybody have a guess what a spectrometer is? It's not just a telescope. Do you want to, since you went already? Yeah, you're exactly right. So it actually splits all the colors up and it gives you each wavelength individually. So when I say wavelength, that just means color. Wavelength and color are the same. So we did not have the nicest images of the eclipse. It's a little bit sad because we went through all this trouble and we have this project that's really fun to talk about. And then when people see our pictures, it's like, oh, well, I've seen better. I could take better on the ground with my camera. And we have this funny line right in the middle of our picture. So it turns out that this is not a picture that is important to our science. This is just a context picture. And all of the light that is here was actually light that was rejected. The light that we cared about went through this tiny little opening. You see the black line there? So the light that we cared about went through that opening. It got split up into all its colors. And what we saw was something like this. So this is false color because we didn't have visible wavelengths. But you see how there's kind of, so you go from blue to red, right? So we see the whole spectrum. And you see how there's kind of a bright patch here and a bright patch here and a bright patch here. Do you guys see those? So those are just the electrons jumping, right? So dropping down and emitting light just at that color, like you would have seen in the fluorescent light if you look through, that's a grating that I handed out. So the way that our instrument did this was actually we had one of those, a much more expensive version. But we split up the light using something very similar to what you guys are looking through. So that's the spectrometer part. So let's talk about the infrared part. Does anybody know what infrared light is? Light we can't see. Is it longer or shorter than light we can see?
Is it the longest?
It's not the longest. There's radio waves and microwaves which are longer, but it is longer than visible light. You're right. So it's longer than red, kind of infrared. That's how you can remember it. So that's what infrared light is. And so does anybody know kind of what the size, rough size of the wavelength is? Like what, it's probably, you can cheat and look here, but what kind of object? Essentially a human hair is kind of on the order of the wavelengths. Or probably maybe 10 times smaller than a human hair. So why are we looking at infrared? So that's the next question. And the reason, there's a benefit to looking at it, and that's because we were looking for these wavelengths to split. Turns out that infrared splits more than visible. So it's just going to give us a better signal on our magnetic field if we can measure infrared. But it's really, really difficult to measure infrared light. Does anybody know what some of the challenges might be before I put them up? You can't see it. Yeah, but our camera can see it. I heard you. No, it's okay. You're right. That actually makes it really difficult to align things, right? It's much easier to align if you can see it with your eyes. But our camera can see it, so it's not too big of a problem. But what else? Does anybody else know? So first of all, infrared light is heat, right? You said it was heat. Somebody said it was heat. That means that everything, this wall and this podium, everything at room temperature is incredibly bright in the infrared. Much brighter than the coronal, way up 93 million miles away. So that's a big challenge because if we don't keep everything very cold to make it dimmer, we're not going to be able to see anything but the warm walls of our telescope. The other big challenge is that the Earth's atmosphere absorbs infrared. So, you can look out and see the sun invisible with your eye, but if you had an infrared eye, you couldn't actually see through the atmosphere at a lot of different wavelengths. So the eclipse actually wouldn't get down to the ground. So, now this explains we're on an airplane, right? So we're flying at 45,000 feet, and we're above the absorption. And so that brings me to the last part. This is an airborne infrared spectrometer. So here's our airplane. So this is usually a private jet. A lot of companies will use this jet, but this one has special windows in it that were special glass, not just that plexiglass that they have on airplanes. So the light comes in and we get a really nice image. And this is a picture of our telescope. Inside this whole thing and this rack are everything that we flew on the airplane. And so I'm just going to go through the parts really quickly, and then we'll get into the fun stuff about the eclipse. So the first thing we have to do is we have to point at the sun, right? So we're kind of looking out a window that's up here, and the instrument's down here. So light comes in, and this mirror points at the sun and aims the light into our telescope. The telescope focuses the light. The spectrometer, as you guys discovered, splits the light up into its colors. And then we have our two cameras that took the two pictures that I just showed you. So what were the biggest challenges? There are really big challenges to being in an airplane. One of them is that, have you guys ever tried to look out the window at a point on the horizon on an airplane? It's kind of moving around, right? The plane is actually moving a lot. So we did a test on the moon. Let me show you what the moon looks like if you don't correct for it. It's just sort of wandering all over the place, right? So if we didn't do anything, we actually wouldn't even have the moon in our camera the whole time. So we had to correct this. So we designed a special system that we tested it on the moon, and it worked just the same on the eclipse. And in a second, hopefully, this is going to snap too. And so that's our corrected image. So what our mirror is doing, 500 times a second, it's going like this to compensate for the motion of the plane. The other thing, I mentioned that things are really bright in the infrared if they're warm. So what do you do to make it darker, do you think? Cool it, right? So we cool it with liquid nitrogen. So liquid nitrogen is really cold. It's like minus, I'm not sure I know it in Fahrenheit, minus 400 or something Fahrenheit. And so this is a picture of us cooling the instrument. So the people at the airport were really terrified. They had never flown liquid nitrogen before, I don't think. And so they made us stay in a lab for about a week before they would put us on the plane. And they were doing things like taking videos like this and terrifying themselves because, the plume was shooting up and hitting the ceiling. And it's just water vapor. But it's nothing dangerous, but they were concerned about it. So the liquid nitrogen is coming in through this tube, and then it's exhausting out here. So there's something else we have to think about if we're making things really cold. And you can think about it. What happens if you have a cold glass of water on the counter, or outside in a humid summer day? What does it do? Condensation, right? Condensation. So if we just poured a bunch of liquid nitrogen on our mirrors, they would just get frosted, and that would be, not good for anybody. So what do you think you do about that? How do you take care of that? Any guesses? Yeah, you put everything in a vacuum. So if there's no water to condense, there's no problem. If you suck all the air out of where the mirrors are, then you have no water in there to condense. So we have to suck all the air out of where the mirrors are and then chill them really cold with liquid nitrogen. And so this big aluminum box is our vacuum chamber. That's what's keeping all the air from condensing on our optics. All right, so now the fun stuff. Ooh, what happened? The fun stuff. So I'm going to give you guys a little tour through what the eclipse was like. All right, so there's our airplane. So 4 days before the eclipse, we went to Chattanooga, Tennessee. Now the eclipse, the airplane was mostly stationed in Colorado. Does anybody have a guess? So the reason we wanted to see the eclipse in Kentucky was because it was very long there. It was the longest duration. Can anybody guess why we wouldn't just fly from Colorado to Kentucky that day? Oh, that's a really good point. As a last resort, so that we could actually get to the eclipse if the traffic was horrible. So then, 8 hours before the flight, we started preparing. So basically, what this consisted of was just cooling. We just spent hours and hours in the morning cooling, so just pumping liquid nitrogen in, trying to get everything as cold as possible because we couldn't fly with any liquid nitrogen. So whatever was in our tank, it was going to be there, and it was going to be, warming up the whole time. And so we wanted to have it as cold as possible. So this is a good time to kind of talk about what it was like inside the plane. You've seen our bench. The window's kind of up here, just out of view, and the light's coming down like this. And so there were 4 operators. This was not an autonomous instrument at all. It needed a lot of hand-holding. And so the operators were doing various things. One person was sitting on the floor here, actually moving the bench back and forth so that you could catch the sun coming in the window. There was one person, I was in the seat back here, and I was actually looking at the camera, the black and white camera that was telling us, where the eclipse was in the window. We had another person looking at the other camera, and then we had somebody who was communicating with the pilots, because here we are in a moving plane, and we had to intersect a moving eclipse, right? And so that was actually a really challenging thing to do. So he was talking to the pilots, and well, I'll talk about this a little later. But I think this was a new experience for the pilots, some of the traffic up there. Oops. Let's keep going. Yeah, so 8 hours ahead, we started preparing. And we took off about 2.5 hours ahead of time. So here we go. So at this point, we're flying to our point, and then we're just going to be circling for an hour. So this was a real nail biter. Everybody was just kind of waiting. We couldn't do anything yet, but we knew that it was going to be crunch time in just a few minutes. And so we're looking out the window at the partial eclipse, and you could only see it out of 2 windows in the plane because it was kind of high in the sky, so you had to look up, and these 2 windows were the only ones. One of them was the window that our telescope was looking out of, and we realized that everybody's breath was fogging up the back window. And we said, okay, stop looking out the front window because, we don't want it to be all fogged when the telescope starts looking out of it. So things like that were happening in this 1 hour, just circling and circling and waiting. And then about 20 minutes before totality, we exited the circle and we started flying along the eclipse path in the same direction as the eclipse. And so this was the really terrifying time. So we had to do some calibrations. We were trying to point the telescope to the sun. We kept losing it. Things kept going wrong. Things that had never gone wrong before went wrong in those minutes. And the whole time we had our one person, the pilot communication person, was every minute was screaming out, 10 minutes to totality, 9 minutes to totality, and we were not ready. And so this was the most panicked I've ever been, I think, in my life, because we had just spent all this time preparing for 4 minutes, and if we missed it, we probably weren't going to get another chance, at least not for 2 years, and maybe never. So, as the sky, I keep doing that, as the sky gets darker and darker, this is just, the pressure just got higher and higher. And so here we can see the shadow. This is the shadow of the moon coming across the earth, right? So it's getting really, really dark, and the eclipse is about to happen. And then it shrinks, the sun shrinks and shrinks and shrinks, and there it is. You can see the little corona. And that's what it looks like close up. And so luckily, by the time we got to this point, about 1 minute before, everybody was seated and ready to go, and we got data for all 4 minutes. And that was it. So you guys feel free to ask me any questions now. That's all I have. Oh, I do have pictures. Thanks. So these are just a bunch of pictures. I'll just leave them up for you guys to look at while you talk. Just pictures of the procedures going on. Yes, and then you.
What are some applications for the data you gathered?
Oh, so that's a really good question. So what the data is going to tell us, we didn't actually measure magnetic field, I didn't mention that, but we didn't have the optics on there to measure magnetic field. What this is going to tell us is how to build another instrument that can measure the magnetic field. So we looked for, remember I talked about those colors that when the electron transitions, we call them emission lines. We were looking for 5. We found all 5. And now we can tell which ones are bright, right, and which ones are dim. So the brightest ones are going to be the best bet for a new instrument that measures the magnetic field, and now we know that. And actually one of the cool things was one of the lines had only ever been predicted, but it hadn't actually been observed, so we made the first observation of that line. So that's pretty cool. It's yeah, quantum mechanics predicts it, but nobody had seen it before. Yeah. You had a question?
Yeah, it was related to that, but what might be an application, and why is it so important to find the magnetic field of the sun?
Yeah, so the reason it's really important goes back to those eruptions that I showed you. If you don't understand the magnetic field in the corona, you can't predict any of the events that are going to happen. We're actually pretty not great at predicting the events right now. We're in the state where predicting the Earth weather was maybe a couple decades ago when you really couldn't trust a 5-day forecast, right? And now it's really good. But for the sun, you can't trust, if a sun ejects, the coronal mass ejection that I showed you in the last slide, if that happens, we're not sure still whether it's going to affect the Earth or not until very close to when it comes. And by then it's too late. So some of the things that you'd want to be able to do is say, shut down the power grid, because you don't want the currents in there wreaking havoc with things and starting fires. Or reroute the airplanes, because you don't want the extra radiation to be, the people in the airplane to be affected by it, things like that. So that's the end goal. It's really, we're not going to do that with this instrument, but hopefully we took a step towards it.
Can you talk a little bit about the team, how long you've been working together? How long was the preparation for this project? Yeah,
sure. So it was actually pretty short. It might not sound short. It was about 2 years of actual, we had the funding and we were putting together equipment. So we proposed about 3 years in advance or so, and the team was essentially, for most of it, it was 4 people, but really 2 people doing most of the work. So it was me, and we had our mechanical engineer, Vanessa, who's right here. She was amazing. She did all of the design, so I designed the optics, and then she designed all the mechanical housing for it, and basically everything mechanical that you see. And we were kind of mentored by our 2 team members here. That's my advisor and her supervisor. And so they were very involved, but at a higher level. But we worked together, and everybody pitched in on the flight, right? And the flight was like all hands on deck. And then we also had a summer student, Alicia, and so she helped me out with a lot of calibrations and things in the summer before, like leading up to the Eclipse. She got to fly in a couple of test flights. And then we had our data analyst, Chad. And there are other people here that didn't fly, but they had a role in kind of building some of the instrument stuff. So I would say like 4 core people, and then maybe 10 people that had some hand in it. We started working together sort of 2 years before, and I think we worked well together, so we were able to get it done.
What really inspired you to study stuff?
Oh, that's a good question. So it actually wasn't the sun at all. It was the engineering that inspired me. So I had a background in engineering, and then I went back to school because I liked optical, building telescopes and stuff like that. And I was originally studying the Earth's atmosphere. I wanted to study climate change, but the group that I was in just didn't have the hands-on building stuff. And I found out about this project that had kind of exactly what I wanted to do, build something from the ground up, fly it or deploy it, and then analyze the data. And so in the process, I've learned a lot about the sun, and I found out that I do like it. It's interesting. But it was really the engineering that drew me. Yeah, so the Earth has a magnetic field. The Earth's magnetic field is much more like a dipole, the standard magnetic field that you see. And that actually acts as a shield. And if you, I don't have a drawing of it, but if you've seen the Earth's magnetic field, you kind of imagine the bar magnet kind of oriented north-south, right? I mean, magnetic north, magnetic south. And then the lines kind of come out of the top and go into the bottom, or vice versa. And so that's why when the particles from the sun and the magnetic field from the sun comes in, it hits the magnetic field of the Earth and then goes to the poles immediately, right? So the poles are where the magnetic field gets very close to the surface of the Earth. And that's why the polar routes in airplanes are a bigger problem. That's why you see the aurora only at very northern or southern latitudes. And so the Earth's magnetic field can protect it. It does protect it. But depending on how the magnetic field that's coming from the sun is oriented, it could actually couple in and make it worse. So that's kind of interesting too. It's one of the things we'd like to be able to predict. Is it going to be, you know, a really bad one, or are we going to be fine? Anybody else?
Jenna, could you talk a little about moving from high school to engineering at Penn State? How did you, what attracted you, and how did you do in those fields?
So in high school I liked math and science, and I didn't really know anything about engineering. But I knew that the engineers used math and science, so that's why I chose engineering at Penn State. It might not be the best reason. It turned out to be a good fit for me, but I didn't realize from the very beginning that it would be. So I went to Penn State, and I was an electrical engineer, and I found that I wasn't sure what I wanted to do when I graduated, and so I stayed and I did a master's, and I realized that I really liked doing research. And so that was sort of at the point I got my master's, I kind of had more direction. It took all the way till then, so you know, if you don't know now, that's really early. So I got my master's and I said, oh yeah, I really like research, I like building things. I'm gonna look for a job that does that. And I got a job, and then when I decided to go back to school, I knew I wanted to focus on, you know, kind of building stuff in the lab, and but also with some science involved. I didn't want to just be building stuff and not know what it was for. So it didn't matter whether it was the sun or the Earth's atmosphere, but I wanted to have both engineering and science. Yeah?
Can you talk a little bit about how this would apply to climate change? I know you said you didn't actually work on climate change.
So this doesn't in particular apply to climate change.
Right.
It is about the sun, but it's the solar corona. And there's not actually much light getting from the corona.
In terms of flying up in the atmosphere and analyzing what
are
you potentially going to work on with climate change?
Okay, so there's a lot of, so there are a lot of instruments that fly up and measure things like carbon dioxide and greenhouse gases, right? And so airplanes and satellites as well. So I'll tell you about a similar project I might be involved in the future, and that is to measure methane. So methane emissions from fracking and from wells on Earth. If you had a satellite, so methane actually turns out to be everybody knows carbon dioxide is the big greenhouse gas, right? That's the one you think of. But it turns out that methane actually, although there's less of it, has much more warming potential. Something like 40, I don't know the number, but 40 times the potential for warming because of what it can absorb as far as heat goes. And so if you can measure methane, that would be really interesting. And it turns out that an instrument similar to this, not the same exact thing, but a spectrometer, can measure methane. And the way it works is it's the same kind of thing with electrons moving around, right? And the methane has a particular signature which appears at certain colors. So if you build something like this, you can look for the methane signature and then be up in the sky, above the Earth's atmosphere, looking down and actually measure, well, here's a well, how much are they leaking? How much are they losing? And they would care about that too, because that's methane that's escaping that they're not harnessing. So something like that would be a way that you could apply an instrument like this to climate change. Yes?
How might you be able to use this information that you gathered about solar flares and all these other eruptions on the sun to be able to harness energy from the sun better?
Oh, that's a good question, and I'm actually not sure what the answer. I don't doubt that this information will be useful eventually. Just getting a better understanding of how the sun works, because it's a big energy producer, right? That's what it's doing. It's doing fusion. That'll definitely play into future energy, but I can't see the path right now. I don't know. And it might be that somebody else could think of a direct connection, but I don't know.
Have you faced any challenges as a female scientist?
I've actually been pretty lucky, I think. I've had a really good experience as a female scientist. I've had, or a female engineer. I was really a female engineer for most of the time. I've had good mentors, and yeah, I would say that I don't really have any horror stories. I work with a lot of men. It's definitely still very male dominated. It's not like it's equal numbers at all. But everybody's been very accommodating, and not accommodating, that's the wrong word. Most of the people that I've worked with, it hasn't even been a thing, right? It's just, well, this is a person who can do the work that we need to get done. So, let's put her where we need her to be, not, oh, she's a woman. Yeah, so I've been lucky that way.